Welcome, everybody. Thanks for joining today's session in the Extreme Performance Series. As always, we're going to be talking about performance best practices. My name is Mark Achtemichuk, better known as Mark A, and I'm a performance engineer here within VMware's organization. I've been doing performance in some fashion within VMware's set of teams here for over 11 years. I have my VCDX and very active in the virtualization community.
Hey, my name is Valentin. I've been with VMware since 2009 and I work in global support services in the Premier Services division, and I mostly focus on resource management and performance, and still a little bit on Windows internals. So today, we're going to talk about NUMA, right? The age-old question about topology, so CPU topology, NUMA topology. We'll also talk about AMD Zen, well, mostly Zen 2, but actually, we're going to talk very little about that. There's other sessions that talk about it a lot more, and the other two topics kind of blew out a little bit. So we're getting into a lot of detail in the other two topics, so that left very time for AMD Zen, and we want to finish on time because there's a lot more presentations out there that you want to watch. The Performance Best Practices Guide has been out for multiple versions of vSphere. 7.0 has released recently, and you're definitely encouraged to read that in total, because what we're covering is really only a minute subset of what is in that guide. We try to cover different topics every year. So instead of going through many different things and repeating them every year, we go through different ones. And you're very much encouraged as well to watch the recording of those presentations. They were not video recorded, so you won't see our mocks as up close as you do right now, but they're still fairly interesting even a few days later, I'd say. With that, let me pass back to Mark.
Okay, so let's talk about NUMA or UMA or both of the topics, and let's reset a little bit on terminology here. So what's really important? So what do we have up on the screen here right now? We have a fancy motherboard. And what we want to talk about next is, let's say we populate that motherboard with some memory DIMMs. Right next to those memory DIMMs, we're going to populate a processor socket or package. And together, the combination of those two is what constitutes a NUMA node. But what about the case where we use something like a sub-NUMA clustering or a cluster on die, and now we have a partial set of memory assigned to a partial part of a socket? What's really important to remember here is that a socket doesn't necessarily designate what is a physical NUMA node, right? Depending on those configurations. So that's important, and a lot of people kind of overlook that or misconstrue how those things are connected. And so what else is important on the motherboard here too? Well, when we talk about the processor packages themselves, we have some interesting things in there like the caches, the last level caches, and the dies and how we attach the dies together. And you'll see differences amongst those between the different manufacturers. So as we kind of wrap these things together here, it's important to think about all of those constructs. So why do we care about memory access latency? So let's dive a little bit deeper into, processor package itself, right? And here we got a kind of a cool heat map where we can see a lot of the components and what's actually happening. But let's take that zoom back out here and look at the various pieces of memory that we can access from the processor. So if we're to take a look at instructions from a core to our first level cache, or L1 cache, typically a very small cache and very fast memory access, right? 1.5 nanoseconds at a very light cost. Next, we can access the level 2 cache, right? Typically a little bit larger, but here now it takes a little bit more effort and cycles to access that, and latency is a little higher. And we push a little bit further out, we get our L3 cache, which is significantly larger a lot of the time, but uses, again, a number of cycles to access it with yet a greater set of latency. And then last but not least, our favorite, where we can go ahead now and access the DRAM through the memory controller. Here we can access gigabytes to terabytes of memory at our largest set of latencies. So when we think about all of this, what we want to do is we want to leverage those fast latencies where we can and do smart things with that. And that's exactly what the vSphere scheduler is doing. We're going to take advantage of all of this topology to our benefit where possible. So another step back, let's go back in time here and talk about when kind of UMA turned to NUMA, right? When the idea was born. So originally, right, all processors accessed memory through a north bridge, and that made sure that all of the memory access latency was uniform, depending on, again, where you asked for it, we all had to pass through the north bridge to get it. So this obviously became a bottleneck in architecture, right? Not very efficient. So again, processor manufacturers went out and said, oh yeah, let's put local memory to each of the processor packages. So now it's, again, with its own integrated memory controller, very quick latency-wise to access it. But what if we have to access memory remotely? Well, they, again, have these cross connects in place, so another core can go access memory from somewhere else. But again, latency of traversing that will a little bit larger. And that's a one-hop scenario. What about two, where now we actually have to traverse a two-hop scenario to get to that remote memory? Again, latency continues to rise. So here's just an example of what that would look like, be it local, adjacent, or routed memory accesses with regards to latency. So you can see it's a very diverse mix. And so again, we want something to take advantage of that. And again, the vSphere set of schedulers do that. So again, an evolution occurs. We add some more crossbars between these processor packages, and now everything is either local or adjacent. And so you can see, certainly that made uniform access of memory a little bit easier, although, depending on processor class, kind of increase those latencies a touch. So why is this all important? Well, it's important to understand NUMA and, again, how these latencies are impacted by the potential architectures. So let's look at this at another example from the guest perspective. So here now we've created a VM, and it's a 16-way VM. And it's misconfigured, or we should call it suboptimally configured, as 8 vSockets by 2 cores per socket. And so what we see here is what the guest operating system sees. So we see 8 NUMA nodes and 16 vCPUs. And when we take a look at that, what we really see is that the memory is highly fragmented. Because of all of these NUMA nodes, we're taking all of the memory available to this VM and having to pass them through too many NUMA constructs. And so it makes it very difficult for the OS and the application sitting on top to make good, intelligent decisions to fit memory where available. And so this fragmentation is going to come at a cost. So this is why we kind of consider this a suboptimal configuration. So what's really important is that we work towards ensuring that that presentation is correct, because the correctness of that VM configuration is going to help optimize the OS's consumption of it, and thus the application stack on top. So again, we take that same example, 16 vCPUs, but now we configure it like physical. So now that it shows up as 2 vSockets with 8 cores per socket, and we have 2 NUMA nodes, right? So this is the most accurate presentation for that VM that we can give based off the underlying architecture, and it gives many more larger opportunities to, again, fit and schedule everything in as required. So now there's less cost and less effort required to do this. And again, that comes from both our side and the operating system side as well. So how do we get this right? So if we watch back some of the earlier presentations, you'll see that vNUM has changed over time. The configuration's changed over time. And so what a bunch of us did is we tried to distill down these idea of configuration principles. And if we follow these configuration principles, this logic here, you're going to get the optimal presentation generally all the time. So let's break it down. So while you've seen and come across many advanced NUMA settings in the community and other presentations, stuff like that, only in rare cases do we need to change those from default. So please don't get in the habit of just getting in and changing things unnecessarily. Now, when we configure the virtual machine, that vCPU count that we give it should be reflected as cores per socket until we either exceed the physical core count of that physical NUMA node or the memory associated with that physical NUMA node. And we'll do some examples in the next slide here to kind of solidify that. Now, when you need to configure more vCPUs than there are physical cores in the NUMA node, or you have to assign more memory to that VM than is available in a physical NUMA node, we want to evenly divide the vCPU count across the minimum number of NUMA nodes. And again, we'll look at an example to solidify that. Here's one too. Don't assign an odd number of vCPUs to the virtual machine when you've crossed over the vCPU count or the physical or the configured memory of the physical NUMA node. And last but not least, again, a lot of people forget this, if you enable vCPU hot-add, you actually disable vNUMA, right? So we don't pass that presentation along to the VM. So be cautious with this, because we see a lot of folks accidentally add these or intentionally add these to templates in their provisioning systems. And then they don't realize that as the VM lifecycle goes on or size increases, that in fact they aren't getting that benefit of vNUMA presentation. And here's a safety net we throw in at the bottom. This idea of don't create a VM larger than the total number of physical cores in the host, with a little asterisk, which means unless you know what you're doing. And the reason we throw this conservative safety net out there is that idea of if you build a VM to consume the whole host, you're not necessarily going to think or capture some of the capacity required to do work on behalf of that VM, right? Our worlds or ancillary services like HCI, and maybe possible security postures with not having hyper-threading enabled for scheduling opportunities, depending on what position you're in. So be cautious when we start to create VMs that are the size of the whole host or that exceed that physical count, because you have to be very careful with those configurations or you're going to suffer from contention quickly. So let's take a look at a couple examples here. So this vNUMA chart, again, if you want to hit the URL redirector down here, there's more detail in the blog post entry. But what this kind of shows here is, let's take an example. This system right here is 2 sockets, 10 cores per socket. It's an Intel-based platform. So with hyper-threads, we have 40 logical threads there. And you want to create a 10-way VM. If you just use the default GUIs and even some default scripting, what gets created is a VM that has 10 sockets. But what you should be creating with an additional step is to make sure that you have 1 vSocket by 10 cores per socket. Again, we want that presentation correct for the guest OS and the app stack. Things like Microsoft SQL Server Soft NUMA will change its configuration based off of what it sees for core depth. And then there's that idea of that odd number, okay, 11. Can you create 11? Yes, you can, but it's a suboptimal configuration, so it shouldn't really go there. So we want to bump that count up to 12 vCPUs. And once we create 12 vCPUs, remember, we've exceeded that physical core count. So we want to do an even divisor. We want 2 vSockets by 6 cores per socket. And that gives us resulting 2 vNUMA nodes. So here we can start to see the logic a little bit more visually that we should be creating these VMs with. So the idea here is to create the most efficient presentation that is like physical as possible. And so the next question I often get asked is, okay, Mark, maybe I've started creating these things or they've taken on life of their own and I don't really know what my environment looks like. So I got together with one of my peers, shout out to Mark McGill here, who created this fling called the Virtual Machine Compute Optimizer. And what it does is it goes out, touches vCenter and goes and reads a lot of information. It creates a report for you. And what it shows you based off of that logic and those configuration principles is what your VMs are configured as today and what they should be configured as for that optimal presentation, taking into account what's available on the host and also taking into account the cluster. If you have mixed hosts within a cluster, you want to configure that to be kind of like the weakest link in the chain. So it's a great quick tool to go scan your environment to show you what you have and to show you how many you could benefit from optimization on. So again, go check this out. It's a VMware Fling and publicly available on the website. So let's talk about a couple of examples, and a shout out to Valentine here for providing some of the data around these couple of use cases we'll talk about. And let's build out and take a look at what we see on the screen here. So first of all, let's lay some ground. This host that we're looking at is 2 by 18 cores. We have no hyper-threading available. The VM that we're looking at is a 1 by 18, right? So we've configured it as an optimal presentation, 18 cores per socket, right? All the memory fits within a NUMA node there. And there's no other VMs on the host. So we have 1 VM that should fit into a physical NUMA node with nothing else running, but yet on the screen here, we're looking at CPU latency, which is a derived form of contention. And Valentine's going to talk more about kind of ready times and contention shortly here, but it's a form of contention. Why are we seeing contention? Especially when we see used of this at not quite the capacity that the VM is configured for. We wouldn't expect to see that. Another interesting detail around this is the fact that, well, we're using vSAN and NSX, right? So we have some software-defined overlays on this host as well. So let's peel back the layer and find out why this is kind of occurring. Turns out that when we look in a little more detail here, we see that in fact this VM is very IO intensive, right? So it's doing a lot of IO. And that means we as system worlds are doing work on behalf of that VM. So if we take a look at the system time here represented in this chart, we're using somewhere between, three to 5 cores, probably on average, about 3 cores worth of that host doing our own system work. So that's interesting, okay. So now what we do as a result of this for efficiency is the worlds in which we're doing some of this IO, we try to schedule within the same NUMA node. Because if we can keep those processes together, we can benefit performance-wise, from scheduling that. But obviously now we're creating some contention. And so what we found here was the fact that because the VM was sized to consume the full NUMA node, because it was a great consumer of IO, and we were trying to do work with it, it was contending. And furthermore, what we could see happening too was the fact that we were doing a number of NUMA node migrations, right? So the idea here is it's costly to do that, but we were thrashing this back and forth, trying to schedule all this stuff in contention. So certainly this was a suboptimal, process by which performance was going to be impacted. So we're going to investigate a little bit more and spend a little bit more time optimizing, the vSphere platform to deal with, this migration scenario and stuff like that. But in the meantime, the situation was able to be successfully resolved. And let's talk about kind of how we did that. So this application was Microsoft SQL Server, so arguably a great consumer of NUMA. And we took that configuration of 18 vCPUs and we turned it into 20. And what that did is that created a wide VM. So now that VM was supported by two NUMA clients. And because of that, we never did see that utilization system time problem again, but we basically prevented it from ever happening again because now we left capacity on each of the physical NUMA nodes for work on behalf of, and because we spread it and NUMA, the application stack was NUMA aware, there wasn't a lot of problem in doing that. So again, kind of future-proof that configuration just by increasing the size of it to distribute it a little bit further. So quick, another little example here too, ready woes and tidy nodes. So if we look at this chart here at the bottom and we look at ready time, and again, Valentine's going to talk a little bit more about that in depth. The idea here is a customer called and said, hey, we see ready time and we see ready time that's crossing one of our thresholds, and that concerns us because you tell us ready time contention is a bad thing. So let's break into a little bit more detail what's going on here. So this host was 2x4 cores with hyper-threading. Now this is a very current processor, platinum grade type processor, right? So the idea with the lower core count is higher clock frequency. And again, that's available in lots of Intel SKUs, right? You can make that choice. And so this wasn't some kind of old processor being used. The VM was 4 vCPUs, right? So here again, the notion of the VM should be fitting within a physical NUMA node or within a socket and package. But we saw this minimal and intermittent ready time. So again, peel back all the various layers of what's going on. The ready time wasn't as bad as it potentially looked. The impact wasn't significantly high, but again, the concern came from where was it? Why do we even see this? And again, nothing else on the host, single VM on this host. And you're quickly going to say, what about all the overlays you just talked about, Mark? Well, in this example here, we didn't have HCI, we weren't using software-defined networking. What it turned out to be was the fact that it was a third-party agent, again, contending. And as we peel back the various layers, we'll take a look at why we saw some of that. So digging deeper, we can actually see on the host here that they had sub-NUMA clustering enabled, which meant that each package defined itself as 2 NUMA nodes. Right, so here again, that idea now that we're pushing out, we're creating these smaller NUMA nodes, and it's more difficult set of opportunity to put everything in there. Since the VM wasn't NUMA aware anyways, right, so it's not benefiting from this idea of the smaller NUMA nodes, we came back with a couple of recommendations. Support came back with the idea of obviously, we can turn off sub-NUMA clustering, probably not required. And we can also, again, expose to the VM that idea of it being a single NUMA node. And what, again, the challenge was here is that in configuring it in this fashion allowed the VM to consume its physical NUMA node. And the schedulers are smart enough now to say, well, because I don't have smaller pieces within that physical NUMA node, I'll probably have less scheduling attention. I'm going to push these third-party threads to the other side. So again, just some interesting scenarios to kind of understand and take a look at. Now, again, that was a very quick look at NUMA. If you want more detail, I highly suggest checking out Frank Denneman's session here. He's going to be doing 60 minutes on NUMA, and it'll be like a deep level submarine dive on it. So definitely awesome content here to check out as well. So next up in the agenda here, the idea of Intel and AMD. So at the forefront of a lot of conversations nowadays is, AMD coming back to the market. Interest in AMD, AMD's various architectures. Well, we talk about Intel and we know Intel so well. Let's just spend just a touch of time here kind of AMD. What's really important here to remember is that, again, with the VMware vSphere technology, the idea is you shouldn't have to do many things different because we are for you on behalf of that. So we're spending a lot of time taking a look at obviously the varying architectures and running our own tests and experiments and optimizing things. So where do we want to start here? Well, first of all, as we look towards AMD Rome, which is arguably the more interesting set of technology that'll be coming to market, you're going to need to be on vSphere 6.7 U3 at a minimum. And in fact, we have many more optimizations, in the vSphere 7 platform kind of going forward. So as you look towards making investments potentially in the AMD technology, you'll want to stay in the vSphere 7 stream to take advantage of that as we continue to optimize scheduler and scheduler behavior. As we talked about NUMA node size, what's interesting in this platform and architecture is the fact that NUMA node size is configurable in the BIOS with the NPS setting. Right, so here now we have some opportunities as we look at the core complexes and interleaving a memory and things like that, and changing the NUMA node size depending on the application and the size of VMs and how we want to consume that architecture on top. Right, so spend some time understanding those and the implications and making sure that the hosts are optimally configured. And then when we talk about power management, what's really important here too is, again, yes, we want to use power management. We want those deep C states because A, that's going to give us still that clock frequency boost, and two, be highly energy efficient. So again, a lot of those same processes and applications where we talk about the idea of energy efficiency and getting some of the benefits from that apply in both the AMD and the Intel worlds, at the same time. So power policy. Just a quick shout out to kind of what's happening in this space. So, AMD platform lands on your dock, right? You have your dynamic policy configured in BIOS. And so certainly now we want to use ESXi balanced on the host side, and whoa, we're done, right? Whoa. Just hold on a second here. That's not really necessarily the best configuration here yet. What we want is we want the dynamic policy change to performance first, and then let's apply our ESXi balanced on top of that, where we can take advantage of at least the deep C states. That's going to give us kind of that optimal configuration, again, for power versus performance. So a shout out here to some of the work that's been happening. So as we look at the AMD, the Rome platforms, we've been looking at it with a number of various workloads, database, right? Our VM benchmark here as well is looking desktop line and stuff like that. So there's some great blog articles here. So pause the recording here at this point and grab some of those links so that you can take those and go look at the detailed information as we continue to look at and evaluate those platforms for configurations and optimal performance. And with that, I'm going to turn it over to my peer, Valentine.
All right. Sorry, I was on mute. Most quoted ever. So I'm going to talk about ready time. We're going to do this pretty much until the end of the presentation. I'm not really sure when we started this, so I hope we're going to stay in the hour ballpark mark, unless you checked what time we actually started the recording. In any case, by the time I'm ready with you, you're going to be ready for more coffee, because this is only ready time for the next approximately half an hour. So we've all seen this. By we've all seen this, I mean we've all seen the HTML5 client and using it, right? And we all know about the advanced performance view. I'm waiting for some sort of nods here, but given that those won't be happening for another 3 weeks or so, I'll just continue on. but what does this tell us, right? So this is a full screenshot of the advanced performance view, and all we've seen is that it's over 9,000, right? 9,000, is that a lot? It's obviously a massive number, but is it really a lot? As going with tradition, this is another slide that took me way too long for a joke that actually isn't all that good. In any case, we've seen over 9,000 millisecond. What else do we see in the screenshot? We see the sample interval, we see the object type, we see the metric, what type it is, the roll-up, the unit, and the values. But what does it actually tell us? Does it tell us the impact? I'd argue it doesn't necessarily, and we need a lot more information to actually judge the impact. So what is ready time and how is it measured? Let's start off by a little bit of CPU accounting basics. Well, it's not really basic, it's too advanced for basic, but those are the basics of accounting, even though they're advanced. So CPU can be in a state of running or not running, right? And we further split the not running into descheduled. And one is when the guest, specifically when the vCPU, when an idle thread is executed, it's called halt. The ESXi host will deschedule that. What's the other part? The descheduled waiting on something. If we split that further, we see co-stop, ready, and VM wait. Those are other states that are not induced by the guest. So basically, the guest itself, when it idles or when it's waiting on something, that is what is called wait in ESXtop nomenclature. If you haven't seen ESXtop yet, you should definitely have a look. There are tons of good blog articles out there, or even presentations in probably this year and former years. You definitely want to get your hands on an ESXtop, because this is the nomenclature I'm going to use moving forward with only some comparisons to the UI. So VM wait and idle together is wait. That's important because many people say wait is high. That means, I don't know, storage latency is high. That's not really accurate. Wait does include idle. So if you're looking at vCPUs, it is not all that an important metric. VM wait, on the other hand, is what you want to look at. Co-stop is when certain vCPUs move faster along and other other vCPUs are blocked on something, whether it's ready or VM wait or another resource. And then we basically have to stop the VM to pull it in so it runs within its queue. All the vCPUs run within its queue. And while this is not really strictly necessary for correctness reasons with most modern operating systems, it is still giving us a lot of performance. So if you think co-stop is actually costing you performance, if you see co-stop and saying, wow, that is pulling down my performance, if you wouldn't have co-stop, it probably would be worse, right? And then ready time, if something can't be scheduled because there is no context to execute on, we see ready. Now let's actually zoom in a little bit on that. The CPU states that we have is when a vCPU comes to life, it starts anew, but fairly quickly it will be added and be in a run state. Or alternatively, it starts in a ready state if it can't run. Going from run to ready is also called descheduling. And when we then ready, we can dispatch again to a running state, and we wait to a wait state. Everything seems fairly straightforward, right? From a wait state, we can wake up, we can co-stop, we can co-start from a co-stop, and we can wake up from a wait. This is it. Those are the CPU states, with the exception of actually killing the vCPU, and then it ultimately gets reaped at some point. But those are the scheduling states. Anything else, I call it counting. Now, don't quote me on that, because it's not really an ideal comparison. It definitely lacks in some states, but this is what is the relevant state of the vCPUs. So if we put this together, right, I want to call out that swap wait, NESXtop, is just another wait state. So it's a VM wait state. And actually there are tons of different wait classes. And these are all part of VM wait. Now we only call out swap wait as part of those wait classes. So in theory, there could be a bunch more, but they're not on ESXtop, they're advanced metrics. It's actually kind of hard to get to them. And there's tons of actually subcategories within those classes. So swap wait, part of VM wait. All of the events that, for example, the monitor could be blocking onto, that is captured by VM wait. But let's zoom in on the part that we want to concentrate on, ready. And in ready, we have a part that is called max limited. It is part of ready. If ready is 20%, it's perfectly possible that max limited is 20% or 10 or 5. And that is the time we spend waiting for execution because of a limit, either on the VM or a resource pool. Then the remainder of ready ready is the time spent because we waited for pCPU to execute on. So not because of a limit, but simply because of contention. Now that could be share-based or induced in any other way, but we have to wait on a core to execute on. We're ready to execute. We could get work done, but we can't just run anywhere. So we're ready to run. Now, what is very little talked about is that there actually is a sliver of ready time that we do scheduling decisions in. So that is happening every single time a VM is dispatched or vCPU is dispatched, and we need to schedule it somewhere because our scheduler needs some time as well. I mean, it's highly efficient and it needs very little time, but it needs some time to make these very advanced decisions and or to schedule. Now, this is not an issue, right? Because it is a minuscule amount of ready that is being needed to run and idle, and a little bit of ready, run, idle. So it goes under and is not noticeable. Now, where it might be noticeable is if you have an application that is super wake switch heavy. So if it wakes up very often and goes to sleep very often, does minimal amount of work, yields, idles, is woken back up. So if that happens, right, then you might see that the amount of ready time because of scheduling actually is increased due to the massive amount of wake-ups where we have to decide what we're going to schedule. Now, this is fairly rare, and there are ways you can combat that, but it felt necessary to call out. All right, so we're back in our vCPU state overview, and let's go into the accounting part. In an ideal world, CPU usage would be the same as run, right? And run, by the way, a different name for it is utilization, right? So the difference between usage and utilization is very, very important because usage is a qualitative metric, right? That qualitative metric is actually showing you throughput normalized to a single core at nominal frequency. What does that mean? Well, we're going to go into that again in a little bit. But in an ideal world, usage should be run, right? The time you spend on a CPU running, that should be your usage. Again, it would be if there weren't any interruptions, no hyperthreading, no frequency changes, nothing, right? If that would be the case, then yes, we would be here, but that's not it. We have overlap. So basically, when a vCPU is running and the pCPU receives an interrupt and has to handle that interrupt, dispatch service routine, blah, 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 that takes time, right? And hopefully not a lot. In most situations, very little, but on a very packet-heavy, IO-heavy world, that actually could be at least noticeable. Hyperthreading. Right, if you have to run 2 threads on the same core, you're now contending for shared resources on that core. You don't just double your performance, right? Just because you double your threads doesn't mean you double your throughput. And we kind of had to find a way to show back the benefit, but also the impact, because there is an aggregate benefit of hyperthreading, but an individual impact. And that individual impact, we have to deduct that from the vCPU usage somehow. So ultimately, we approximate 25% of benefit for running hyperthreading. So if 2 threads or 2 worlds run at the same time, both of them together do 125%. That means each does 62.5, meaning 37.5 will be deducted from usage if another world is running at the same time. And then there's the frequency, right? You should be running above the nominal frequency if everything is configured right, but if it isn't, or if you have a thermal issue or PSU went down or maybe a bug somewhere, you might be running below nominal frequency. And we also deduct that from usage. Now, this latency, right? This stolen time, co-stop ready, but not max limited, right? Just co-stop and ready, not the total ready. If you have some ready time because of a limit, that is not part of lat-C or latency or contention. Overlap, hyperthreading, frequency scaling down, co-stop ready, that is lat-C, and that is what Mark was talking about earlier. So that is a sum of all kinds of contention. It's not all contention, it's not limit-based contention, but it's what we internally call stolen time. Not the same as steal time on Linux. Steal time on Linux is basically just ready time. And then, if we configure everything correctly, power management policy and so on, usage should go above the nominal frequency, and you should actually be issuing more non-halted clock cycles than you spend time on the CPU because you're running above the frequency. Now that means that then usage will grow beyond use. Now we also charge sys to usage or to the VM. So basically if a VM does IO, we need to charge that CPU cost to the VM. And the only way to do that is either if a world within an IO world within the VM is in that scheduling group. But if it's like a shared world outside, if it's a poll world or something else that potentially multiple VMs share, it's somewhere outside of the VM, right? And the CPU cost there has to somehow be charged back. And we basically charge it to the VMX world, which is part of the VM. So that is that sys charge in there. If you're looking at ESX top, and this is really something you should be doing, I mean, since you can pause this, log into ESXi host, and I don't know, we do it run by click. You enter ESX top, and you have a look at what's running there. Now I press capital V here to view VM only. That's what you're going to do most of the time. Although that shouldn't be muscle memory, because sometimes you don't capture things that are not VMs that happen on your hosts. But usually you want to look at your VMs. And if you kind of project the colors on there, you see that most of it is scheduling or state-based, and only a little bit relates to the actual accounting part. If you look at an ESX top though, right, and you see percentages everywhere, and now you're looking at the HTML5 client, and you're checking out, what's this? Millisecond? Why is there milliseconds, right? That doesn't look like a percentage sign. That's not fancy Unicode or something. So where does it come from? If we further look at ESX top, because I just feel very comfortable here in this tool, so I'm going to use it for most of this. We look at a VM and we expand the group. Remember when I said a VM is a scheduling group and it has tons of other worlds? There's one vCPU world here, and there are other worlds: the VMX world, net world for the NIC, the PV-SCSI world for the PV-SCSI adapter, VMX, assist threads, and so on. And we see here, the ready time is approximately 8%. So, but where's percent and where's millisecond coming from? We set the seconds to delay for 20 because the real-time chart in the real-time charts that you see in the client have a 20-second sample policy, and we want to get to that as close as possible. We want to try to see whether we can see in ESX top what we see in the UI by trying to align it. So we do that, and we also look at the actual vCPU stats in VSI. That is basically the source where ESX top is taking the information from. And we're kind of trying to replicate that here, right? We're trying to replicate what host D is or the agent stats is doing when it gets those charts. So we get the information, we're going to sleep for 20 seconds, and we get the information again. And when we look at these counters, they're all absolute. They basically track the time that vCPU has spent time in a certain state in microsecond, right? So if we look at these microseconds and we do a very, very simple math and we deduct them, we see that over these 20 seconds, that vCPU has spent 1,780 milliseconds in the ready queue. If we divide that by 20,000, because 20,000 milliseconds, and multiply by 100, we get approximately 8.9% of ready. Let's look at ESX top and see how close we were. Yeah, close enough. Well, and the thing you have to take into account here is that the sample interval is different, right? We started at a different point and we ended at a different point. Same length doesn't mean you capture the same content. How does it look with my hands cut off? Okay, I'm gonna keep it in here. So this 1,780, looking at the UI, is actually close enough, right? It's fairly close. So that's where it's coming from, that's milliseconds. And sometimes you have to think as counters at something that developed because they're very close in tracking what the scheduler is doing and where the actually source is coming from. They haven't necessarily been developed for ease of use. And we're going to go into some other problems that we have or that you might face with millisecond counters. Now, truth be told, millisecond counters are really, really good for total amounts of time spent and potential throughput or progress lost, right? If you want to count it that way. But there's something else that we can do. If you look at the different summation rollups, right? So we call them real time, last day, last week, last month, last year. You can see that the y-axis is getting bigger and bigger and bigger the further you go. Now, why is that? Well, first, let's actually try to normalize how we call these rollup or how we define them, right? This is the sample interval, 20 seconds, 5 minutes, 30 minutes, 2 hours, 1 day. And it's still too hard, right? So let's look at actually seconds. This is the amount of seconds each sample contains. And here we see pretty quick how many seconds, for example, the real-time sample, 20 seconds, and the last year sample contains. That's a day worth of potential ready time, right? So if you graph out the ready time of a VM, and let's just say it has 5, 6, 7%, the ready time in milliseconds would go up and up and up and up. And you might wonder, why do we go down here at this part, right? Why do we go down past week? Well, because it hasn't rolled up yet. If you look at your absolute ready time stats or any other stat in milliseconds, you wonder, why does it go down again? It should only be going up. Then the reason is that it didn't get rolled up yet. So again, this happens at a past day and so on. So if we graph this out, right? If we graph out a single VM that has a 5% constant ready time, right? Look at that axis. That is getting very big, very, very quick, right? And you see we have 1 vCPU, 2 vCPUs, and 8 vCPUs. We didn't even talk about multiple vCPUs yet, but you can clearly see that multiple vCPUs multiplies the time of ready time if the VM itself has a constant 5%. So if we plot this logarithmically, you can see the massive amount of difference in millisecond time spent in ready, right? And this makes a little bit more sense, but it's really, really hard to eyeball if you don't plot it logarithmically. So in summary, percentages usually beat absolute time, right? Especially for troubleshooting, because usually we want to look at a VM on how much impact something has in regards or in relation to the VM size. We don't really care that we lost 2 minutes worth of throughput or progress to ready time, right? That's not very often a concern we have. We want to see, hey, is this VM running 2%, 3%, 5%, and so on slower? Well, then again, can we actually make that comparison? Can we say a VM is running 5% slower because there's 5% ready time? It's a little bit more complicated than that, sadly. So percentage beats milliseconds for the most part. Okay, so how do we normalize ready then, right? So while you cannot have more than 100% in the pie chart, you certainly can have more than 100% for a VM. And if you look at ES6 top here, you see already far outstrips 100%. Why is that? Well, because our percentage is defined on a single vCPU, right? The maximum amount a vCPU can spend in a ready state is 100%. So if you have more vCPUs, then if all of them would be ready 100%, then it's the sum of all these vCPUs. That is the definition of our 100% per world, right? So we see those vCPUs and they all add up to the number we see, the sum. Now, is that the impact? Is it the sum of all the ready time of those vCPUs what impacts our workload? Actually, not really, right? Because those ready times happen pretty much at the same time, right? So if your VM isn't making any progress, all of the ready time of those vCPUs are approximately at the same time. So that is it. The percentage is the progress that you're not making, the whole VM in total, right? So in relation to the VM, that is what you want to count, the average of the vCPU ready time, not all of it, right? Because if ready time wouldn't be happening at the same time, if ready time would only happen on one vCPU, then what you would be seeing is ready time and co-stop. So it's fairly common that uneven ready time will cause co-stop until all the vCPUs are co-started again. That's why we normalize ready time, because we care about the normalized impact on the VM. Now you're saying, wow, I mean, this is something that I've read about in 2009, and this is still necessary. Do I have to take my calculator out when I'm trying to figure out ready time impact? And yes, actually, it still has to happen. It's still necessary. It's not that hard to remember, and presumably you're looking at this on a computer. So on Windows, you press the Windows key and you type calc, and it should be fairly straightforward. These numbers are not too hard to remember. But there is actually a third-party tool that is being used by VMware people too. And here's the thing, right? If I think that whenever there is like a third-party tool that does something very simple that VMware employees are using, then we probably should look at whether we can do anything a little bit better. And we did, right? But let's talk about custom intervals first, because that's a question that comes up from time to time. If you define a custom interval, it's not in the regular sample intervals, all you have to do is you go into the next larger interval wherever the custom interval fits into. Like the last 2 days doesn't fit into past day, but it fits into past week, right? All very much straightforward. If it's from definition, right, then you have to calculate a little bit harder, but this is approximately 8 days, right? So it's not on the border of anything. So that doesn't fit into the past day, it doesn't fit into week, but it fits into last month's, and that's going to be your sampling. Now, it tells you there, ISO 8601 format. I don't know where it's coming from. Actually, my short date and my regional settings is ISO 8601, and it's not being taken by my browser, in this case, Firefox. I haven't filed a PR, I haven't filed a bug on that yet, but I will. It's not 8601 format, and if it is, it might be a different browser or something else. So don't get confused by that, because I did. So talking about the superior date format, ISO 8601, right? I work in support, and we often get cases that ship around the globe, and we get ESX top batch output, which is UTC, if you quote it on ESXi. If you get it from somewhere else, right? If you use our ESX top, not necessarily. Actually, with RSX top it is. If you take screenshots, they're usually in the browser local. Then people forget about time zones, right? And all of that has caused escalations that drag on for weeks that could have been resolved in days if we all could have agreed on a timestamp, on an accurate timestamp. And ISO 8601 helps with that. Little tangent, but I really just want to call it out because it is so critical, especially if you open a performance case and we have to talk about dates. So there's one other thing that you can do with the custom interval, which is what I'm doing. If your mouse dexterity is high enough, all you have to do is you take your cursor and you slightly move it across the axis, and you see what the sample length is. And you can do that with many other tools. So instead of doing math and figuring out where it fits into, you just kind of check when your mouse clicks and snaps to certain points in the grid. So in this case, what we see is we just snapped from 00 to 30, meaning we have a 30-minute, 1,800 second interval here. So we're in past a week. To let you in on my thought process here is when I was doing this slide, I wasn't sure whether I should make 00 and 30 blue or just the first 0 and the 3, because while the 0 is the same, it's not the same 0. I don't know, a little bit of trivia. In any case, half an hour sample interval. So I mentioned before we should make this better, and we did. And we created readiness. Readiness was introduced in 6.0, and it automatically calculates the percentage. It is already normalized, so to the vCPUs, but it is only available as a level 4 metric, meaning it is available in real time, but as soon as you switch to last day, you only have your level 1 stats available for the VM here, which is ready, usage megahertz, and usage percent. And we thought about putting it in, but we thought about replacing ready, but then that's backward compatibility potentially. And if we just edit, then we increase the load and the cost on the database. So we didn't put it in. And one of the main benefits of readiness really is that you could easily eyeball it over the different periods. I mean, by saying I'm using VROPS anyway, I don't care about that. VROPS is already doing all of that. And you're right. I'm just saying there's something that you can use as readiness if you're looking at real time, which is pretty much what you're going to use your vCenter or vSphere performance charts if you already have VROPS. So how much readiness is too much? And I'm saying readiness here because it's already normalized to a percentage, it's already per vCPU. And you know what? Any traffic light thresholds that you see, like over 10% is bad, that is really just an approximation. And it really depends on what the workload is. And as an example, I'm actually referring to data that we have been showing you if you have seen any of the past presentations since 2015. This year is a Java workload, and it's normalized to 1. And what we're seeing here is a fairly linear drop in throughput. So we have an approximately 18% ready, and we're dropping 15% in throughput. So when you're seeing 5% ready time on a VM, you could be saying, I'm losing 5% of throughput for throughput-based workloads. Now, if you have a workload that is a little bit more latency sensitive, right? And just to be really clear, we're looking at tail latencies. So we're looking at, and actually the 99.99th percentile latencies. So this is 0.01% of the latencies, right? So in these are depending on what the competing workload does, because if the competing workload wakes up a lot, right, it allows the other VM to wake up more regularly, meaning less impact of ready. If it doesn't wake up as often and does the same ready time in shorter bursts, then it potentially cannot wake up as often, meaning the latency will be higher. And the impact here, again, for those outlier latencies is actually 44% if it's spiky and 77% if it isn't. So if you have a latency sensitive workload especially if you care about tail latencies, you should probably look into a reservation, or ready time could have a different impact there, and you should be aware of that. It is workload specific. Long tail latencies. What is tail latency? Who should care about it? Well, in theory, you should care about it. If you have a workload that depends on multiple interactions per transaction, then you should really care about tail latencies, because these outliers, right, depending on how you define tail latency, and we went with a fairly extreme 99.99, depending on how you define this, it can have an impact. If you have 100 transactions, right, then having a single outlier could pull down that whole transaction, depending on how much of an outlier it is. All right, with everything we learned, now we can finally interpret the impact of ready time based on a screenshot that someone sent us via email, right? And if we're looking at this here, this was a third-party tool and a customer example, and they say, I get this report critical ready time, you got to fix this. So we're looking at this, and we got this screenshot and the host log bundle, and we're looking at the columns here, and we figure out this must be host, right? And we see the milliseconds there, ready time. Okay, so assuming that this is for the host, meaning all of the VMs on that host contribute to that ready time. Excuse me. So we're looking at 52 vCPUs, and where we got those from is from ESXtop. It listed right there, or we can get it from SCADstats. We basically just count the amount of vCPUs, and we follow the formula that we had earlier, and we calculate that. And if you want to challenge yourself, now is the time to hit pause and calculate that yourself. I actually don't have to wait because you can pause. But the real-time stat sample length here is the best possible assumption, right? Anything else, and the ready time would be even lower, right? This is the worst case scenario. And even here, the ready time is 0.37, right? There was also like a 10,000 millisecond ready time. If you're assuming there were similar amount of VMs, it would still be very, very little. So I guess the summary here is that you shouldn't trust third-party tools, especially if they can't capitalize a VMware correctly. And for everyone that is watching, it is capital V, capital M, lowercase w, lowercase ARE, right? That's how you capitalize VMware. Okay, now if you ever configure CPU limit, if you're using vCloud Director, if you set CPU limits on resource pools or VMs, what is the impact? Because I very often see, well, the impact is max limited, right? That's not quite accurate. If you have a certain usage and you set a CPU limit, what we promise you is that we will not go above that CPU limit. So basically your demand, your former usage, what you could be using is demand, but you will not use more than a CPU limit. And above that, that's the impact. That's the impact that you have, the difference between the CPU limit and your demand. Now, that is not just max limited. Max limited is our enforcement. But what also happens is a ton of co-stop, because we cannot really max limit everything equally, depending on what's running, of course. So we need co-stop to prevent skew. Now, that's not a bad thing. Again, that's a good thing for you. That's a performance benefit. So, but the difference isn't just max limited, it is usually both together. The one caveat here is that when you look at LATC, CPU contention latency, then max limited isn't part of that, but co-stop is, even if it's the co-stop caused by the limit. That's a little bit of a gotcha there, but in most cases, it isn't really all that critical. And obviously, if you do not exceed, demand doesn't exceed the CPU limit, you'll never notice there's a limit in the first place. Okay, so let's look at a VM here. So this is a 12-core, 24 pCPU host. So hyperthreading is enabled, and I was running a 24 vCPU VM in a busy loop. And you can see there, we're having about 39 gigahertz of throughput. Now first, I disabled Turbo Boost and lost approximately 3 gigahertz. And you can disable Turbo Boost if you allow power management to be presented to ESXi, and then all you have to do is change a little setting. Works immediately, no reboot, no ILO, no iDRAC, nothing. So it's good to follow best practices, makes it a lot easier. Now, and then I set a limit to 28,800 megahertz. Now that is pretty much all of the cores times the nominal frequency of that CPU. And I'm definitely consuming more, right? I see more megahertz consumed there or used, but there was no impact. Well, because that is the benefit of hyperthreading. So all of the turbo boost and hyperthreading, that is opportunistic gain for that VM. right? The actual limitation or resource limitation, that is only counted against the single core at nominal frequency. So once you set a CPU limit below that, you can actually see that max limited goes up, co-stop goes up. And then a little bit later, all I did was disable co-stop, and you shouldn't do that, right? This is not saying, oh, I'm going to get less co-stop. No, no, no. By disabling co-stop, you're not saving anything. It's going to cost you the performance benefit that co-stop gives you by keeping these CPUs executing approximately at the same speed and progress. Okay, so how do you check for CPU limits? Well, again, we go back to ESX top. We actually enabled CPU alloc, and there you can see, once you click enter, the Amax. Right, and one VM here certainly has a limitation of 4,500 something megahertz. I'm a little bit zoomed out here, so I can't tell the number exactly. Accesses time interrupts, right? If you have any guest software that wakes up a lot that can program time interrupts, you can set that as well. And what I didn't tell you earlier, I actually have to disable a few standard fields so I can put them in the screen, or if you have a smaller monitor, you can disable fields as you want, just so you can fit everything in the screen. You can't really easily sort or scroll through ESX top. So if you look at summary stats here, we can see time interrupt, right? And these are controlled by software. So if you have an impact to ready time because your applications all wake up as often as they do, you might want to check out which application is doing that. Like in Windows, you can do that with powercfg.exe, and it gives you a report. On Linux, you can check that as well. Now, excessive wake-ups. Well, if there is a workload that is waking up a lot, not necessarily because of time interrupts, but any other events, whether it's I/O or anything else, you can check the total wake rate in ESX top 2. And remember that example where ready time became relevant because it was waking, sleeping, waking, sleeping so often? You can check that here. Now you see expiration, quantum expirations next to it. That'll always be 0. We actually took that out of ESX top in 6.0 because it isn't really relevant. So now it only displays as a debug stat. And again, more ESX top screens because you can't get enough of them, can you? If you want to look at ready time, or if you're looking at the impact of broadcast and multicast to ready time, then the simplest way to explain is that if all of those VMs, for example, VDI, are on the same broadcast domain, they're all going to receive the frame and the interrupt at the same time, so they tend up to wake up at the same time. Even if the usage isn't very high, right? They try to wake up at the same time. That could cause like short-term ready peaks. And again, the easiest way to check that is in ESX top. Check multicast, broadcast, and you can see, oh, that's definitely a little bit too much and totally not real. I filled these in. Those values are not realistic whatsoever. You can probably see something else, but I really couldn't run a test just for one slide. But it happens. Trust me, it really does happen, and it has happened before. Now, remember the locality example that Mark Earl had earlier? This can happen when we migrate NUMA clients to certain NUMA nodes because of locality to IO context. And sometimes we have thrashing. Now, you can actually check that in chat stats. If you have tons of locality migrations, you might want to turn that off. That often helps, especially if you have few large VMs. If you have many small VMs, it's usually very beneficial. But if you have few larger VMs, it is less so. It still depends on the workload, but it's definitely worth checking out. Doesn't need a reboot, just vMotion VMs off and on, and that is it. So it is not an issue. Very often, ready time is not an issue. We get asked a lot, hey, what's this ready time here in the system world? Why are my system worlds ready? Well, the system is not really a world. System is a group. And that group, if we expand that, contains many other worlds, among them the idle worlds. And idle worlds are ready when something else is running, when the idle world doesn't have a need to run. So ready in a system group is perfectly normal since 6.5. In 6.0, we actually did have an idle world that captured all of them, but obviously no one ever asked why is idle ready, because figure. So just one part here, 6.0 is end of support, right? I hope you are not on 6.0 or 5.5 for that matter. Maybe if you have extended support, you should have a plan in place to get off. So look at the end of support. That doesn't mean end of technical guidance, but end of support, right? And for 6.5, that was increased. So you should have enough time, but don't take too much. Now, amount, right? So looking at this host here, we see 900 something worlds, but 0 VMs and 0 vCPUs. Now, this system is already overcommitted without even running a VM, right? So what do we see? Well, we click on view all. So we don't just want to see VMs, right? We want to see all of the worlds. And we're looking at some of them, and some have ready, right? And we've already learned that ready time can be caused because we have to figure out where we schedule things, or maybe some minor minimal contention that really isn't critical whatsoever. So don't freak out if you see sub% or even sub-some percent ready time, even if nothing is happening. That is usually not a sign of anything going bad whatsoever. Now looking at this here, this is again looking at the UI, and we're seeing 500 something milliseconds ready time. Now, is this bad? And what you should be saying right now is, oh, we don't know. We don't know how many vCPUs that has. Or what, oh, actually, no, yeah, you can see the sample lengths, yeah. No matter how you put it, how many vCPUs that is, that should not be an issue, right? So while this is a 2 vCPU VM and it's about 1.38 ready, while it was idle, even if it was just 1 vCPU, that is still very, very, very little ready, and it shouldn't matter whatsoever. But always check, know the VM size, know your sample. If you get a screenshot sent from this, you know what to ask for now. So how do you remediate that, right? I mean, I just watched you for the better part of 40 minutes. Okay, we're getting pretty close to the time here. And what can I do? Well, if you think it is a ready time, you just reserve the VM, right? And again, in 6.7, that even will guarantee you a maximum core throughput. It will even eliminate hyperthreading. Enable latency sensitivity. If you have a workload that is very sleep-wake heavy, right, you can enable latency sensitivity, and we do all kinds of optimizations to basically not wake up anymore, basically force the VM to run in place and not wake up as often. And we actually talk about this in detail in 2018, if you want to go back to the recording. Now, latency sensitivity high does a lot else, but that's one of them. And then we have hyperthreading, right? If your security policies, and depending on what system you're on, AMD or Cascade Lake, if you can, use hyperthreading. Keep it as at least a reserve, right? And if you have ready time, then you will trade that for hardware contention, but less, because hyperthreading actually does give you a benefit. And last but not least, turn off those unnecessary affinities. If you don't need those DRS rules, if you don't need those CPU affinities, don't use them, right? Hardly will you improve over something. If you're doing for licensing reason, that's a different thing, but hardly will you improve over the ESXi scheduler if you set affinities. And with that being said, there are many other extreme performance serious sessions that are ongoing. Take your pick. You can watch them right away. You don't even have to change the room or anything. You don't have to go, well, you can go for coffee, but you can watch all of them. Mark?
A quick shout out here. Yeah, if you want to look at ESX Top, as you saw all the great screenshots here, right? Go check out the hands-on labs. You can run ESX Top in the labs. You can take a look at some of it there too. So you can do it in a safe environment, learn about the tool at the same time. And last but not least here, there's a performance survey at the bottom. We know you have many VMworld surveys. This performance survey comes back to the performance engineers. So if you got some great feedback, you got a great quib that you want to put out on something, please go and hit this link and hit that survey. Again, it comes directly to the performance engineer. And with that, I think that's our wrap for today. Thank you very much, and I appreciate everybody's time. Thanks, Valentin. Again, excellent creative presentation. Go back, review it, and check out all the names that Valentin put in for the VMs within all those screenshots. I think you'll find that it's some interesting combinations.
All right, have a great day, everyone.